Hello and welcome to Chemistry 101 General Chemistry from Qatar University. My name is Ismail Badran and I am Assistant Professor in Physical Chemistry at Qatar University. Today we're gonna start Chapter 6, which is Thermochemistry. This chapter depends basically on the outcomes of Chapter 5, which is gases, and this is the introduction to thermodynamics. So in this chapter, we're gonna talk about the natures and types of energy. We also speak about energy changes, and that means exothermic and endothermic reactions. We'll introduce you to the world of thermodynamics. We'll also talk about something called the enthalpy of chemical reactions, and finish up with the standard enthalpy of formations and reactions. Some of the concepts of this chapter are new to you, so we're going to walk you step by step into these things. Some of the concepts in these chapters you have already know them in school, and some of them are new to you, so please bear with me to go over these things. First of all, we're going to talk about energy. Of course, energy, nobody can see energy. Energy cannot be seen, touched, smelled, or weighted, but it's recognized by its effect. We know it exists because of its effect. The definition of energy in physics is the capacity to do work. And work is actually force times distance, as we learned in school. There are a couple different types of energy. There's radiant energy, thermal, chemical, nuclear, and there's also potential energy. And the one we are interested in this chapter is actually the potential energy that exists in molecules. So remember that all forms of energy can be converted, at least in principle, from one way to another. And energy can be neither destroyed or created. This is law of conservation of energy. And therefore, the total inequality of energy in the universe is assumed constant. So our universe has some energy in it, and that amount of energy is constant. Now, almost all chemical reactions actually absorb or produce a kind of energy, and this is in general form of heat. So heat is the same as thermal energy. In our case, yes, heat is actually thermal energy, and it is measured in units of energy, which is joule or calorie or whatever. But temperature is different. Temperature is a measure of the thermal energy or the measure of heat. So temperature is not the same as thermal energy. When I say temperature is measured in Celsius or Kelvin, but heat is measured in joules. So actually temperature and energy are not interchangeable terms. Temperature is a reflection of heat. So when the heat is increased in the system or for a system, its temperature usually increases. So temperature is our observation for heat. In this chapter, we're going to talk about what we call the system and the surrounding. So the system is actually the specific part of the universe that is of interest in the study. So for the system, you can imagine the system as anything you like. If you're a chemist, then your system might be a beaker. And this beaker is surrounded by some other things like the air around it and the container and all that. And we call that stuff is the surrounding. So we have the system and the surroundings. The system might be, for example, for somebody who is working in biology, it might be the cell or the slide under a microscope. It might be the cell itself, and the surrounding would be the slide and whatever the air, whatever surrounding that slide. For somebody who's a meteorologist working in weather, maybe the system is as big as the country or the region itself. So, for example, maybe the weather is the Middle East. That's our system, and the other atmospheric systems in Europe and in Asia and India, that would be the surroundings of that system. The system might be the Earth itself, and everything will be the surrounding. And in thermodynamics, the system might be actually the universe itself. So the surrounding is the rest of the universe outside the system. So for our chemical problems here, we care about the small containers that is filled with a gas. That would be the system, and the surrounding, of course, will be the air outside that system. So in this slide here, we are showing a flask filled with some substance. Inside the flask, we can define our system. The surroundings will be the air and anything in the area outside the flask. The container itself can be actually part of the surroundings. So here we define that the system plus surroundings is equal to the universe. So the universe is composed of a system and surroundings. There are actually three types of systems that we deal with in thermodynamics. The first one is called open system. So this is called an open system. In open system, we are changing between the system, so it's open, so the material itself, the matter inside, can get in and out easily. Because this is open, so if there is a gas or there is water, so the water evaporates even at low temperature, its vapor can get inside and outside. So this is an open system. Also, the heat can get out or enter the system through this flask barrier. So if this is made in a glass is a very good insulator. It's not a very good insulator, therefore, when you deal with the glass containers, that's actually, and the flask is open, this is an open system. If you close this system and it's still made of glass, matter here, you cannot exchange matter, but Q can still get inside and outside. This is called a closed system. But if you are changing this glass container with something that is really thick, an insulator, then you will have an isolated system. This is an isolated system, so therefore nothing can change. It's an open system, matter and heat can exchange. In a closed system, the heat only can exchange from the system to the surrounding. In isolated system, nothing will change, will exchange. And this is the system, this is a perfect system actually to study in thermodynamics, because there is no interaction between the system and the surroundings. Now, in thermodynamics, we deal with two things, heat and work. So let's talk first about the heat. If a reaction happens and there is heat or thermal energy, exit that reaction. So it goes from the system is our reaction here, to the surrounding. We call this an exothermic reaction. Exothermic reaction or an exothermic process is a process that is associated with heat release. So the heat gets out of the reaction and goes to the surrounding. In this case, we write the reaction as follows. For example, 2H2 gas plus O2 gas goes to 2H2O liquid plus energy. So this is an exothermic reaction. And in that case, we are expecting the temperature of the surrounding actually to increase. An endothermic reaction is the opposite. A good example of an endothermic reaction is the decomposition of HGO, the mercury oxide, into mercury liquid plus oxygen. This reaction does not happen by itself. It needs some energy to happen. You need to heat it up. That means you need energy to enter the system from the surrounding, and this is called an endothermic process. When we express exothermic and the endothermic processes, we can actually express them in 4 different ways. The first one is you write the reaction as is. So let's say combustion is always exothermic. So CH4 plus 2O2 gas produces CO2 gas plus 2H2 gas. This is a reaction. This is a combustion reaction. So it's associated with energy release. You can write delta H, which is the enthalpy of the reaction. We're going to come up to the definition of enthalpy. It's going to equal to minus 890 kilojoule. So the negative sign here means that exothermic, that means energy or heat, is released from this reaction. The other way to do this is you bring this number into the equation. So in the second example here, you write CH4 plus O2 goes to CO2 plus 2H2 plus 890. Note here that because I move this energy to the equation, this means that now the energy is part of the products. That it means that it is released by the reaction, and now I'm dealing with it as a product, and therefore there is no need to put the minus sign. If you want to put that number to the side, and you want to say delta H is minus 900, so you have to put the minus. For the endothermic reactions, let's go back to case 1 here. For endothermic, let's say 6 carbon solid plus 3H2 gas goes to C6H6 to form benzene. This is the formation of benzene reaction. This is endothermic. So delta H for it is plus 83. If you want to bring this number to the reaction itself, this is an endothermic. That means the reaction will absorb heat and you put it in the reactants. So in that case, 6C plus 3H2 goes plus that 83 kilojoule will produce you benzene. The other way to do that is you write the enthalpy as in terms of molar enthalpy. So you say, for example, minus 890 kilojoule per mole of methane. And we will come up to the difference between enthalpy and molar enthalpy later on in this chapter. But the other way to, and the most important way to express exothermic reactions endothermic is by an energy diagram. So in case number 4 here, we are having combustion reactions where methane is reacting with oxygen to form CO2 and H2O. In an exothermic reaction, always remember that the products are having less energy than the reactants. So products have less energy than the reactants, and therefore they are more stable. In endothermic reactions, it's actually the other way around. So, just going to come up to definition of internal energy later on. So this scheme here is for an exothermic reaction. We are looking at the left side here. In the left side, for exothermic, if you are bringing 2H2 gas plus O2 gas, that's the reactants, to form the products, which 2H2O liquid. This is an exothermic reaction. So the reactants are higher than the products, and the energy difference between them will be released by the system to the surrounding. This is an exothermic reaction. In endothermic reaction, it's the other way around. So again, for the decomposition of mercury oxide to the right here is your reactants, and it forms products, which is the mercury and the oxygen. This reaction is endothermic, so somebody has to pay price for this. So the surrounding, in that case, the surrounding will provide some heat to enter the system for this reaction to happen. So this is just a picture from the history. Actually, in the old days, they were using balloons to travel, and this one was containing hydrogen fuel. So they were trying to combine fuel with hydrogen with oxygen to form liquid water and benefit from the heat, but unfortunately this went wrong and there was an explosion. So this is a very combustion reactions usually are exothermic, and nobody is using these balloons anymore. For endothermic reactions, an example, for example, is this mercury oxide decomposition, as you see here. It's endothermic. That means you need to provide heat for this reaction to happen. So in this case, the mercury oxide is inside the test tube, and mercury oxide does not decompose by itself. So you need to provide heat from the surrounding. In this case, it's the Bunsen burner. So the Bunsen burner is your surrounding. You provide heat to the system in order for this reaction to take place, and that will produce you a mercury liquid and oxygen gas. Now, let us introduce you to the world of thermodynamics. Thermodynamics is the study of the interaction of heat and other kinds of energy. So in thermodynamics, we'll focus on the system, not in the surrounding. However, also studying the surrounding is important, but usually when we talk about things, we talk about the system. And there are actually 3 laws of thermodynamics. It's the first law, second law, and the third law of thermodynamics. Before we go further into the laws of thermodynamics, we need to define what we call a state function. A state function state functions are properties that are determined by the state of the system, regardless of how the condition was achieved. So the definition of a state function is actually it's a path independent, so it does not depend on the path that is taken. Examples of state functions is the energy, which is U, the pressure, which is P, the volume, which is V, and the temperature T. So let's say that we have a system that is changing temperature between T1 to T2, or T initial to T final. In that case, we say delta T is equal delta T final minus T initial. If that system is changing volume, as we studied in chapter 5, let's say this system, we have a gas container that is having a V initial, and that V is changed to V final. So we say delta V is equal V final minus V initial, and so on. These are all state functions, and therefore we don't care about the path, the volume it took to go from V initial to V final, or the temperature, or so on. Because this does not depend on the path, in that case, it's a state function. Not all functions in thermodynamics are state functions. There are some that are non-actually state functions, and they do depend on the path, and we're going to show you this in a few seconds. To visualize what a state function means, let's imagine here the distance. Distance is actually a state function. So imagine we have two hikers that they want to go from the bottom of the hill here to the top of the mountain. They want to hike their way up. Hiker 1 can take one path, and hiker 2 can take the other path. Now, for the vertical distance these hikers took, it's actually distance final minus distance initial. So the vertical distance is the same for hikers 1 and 2, and therefore the vertical distance is actually the direct vertical distance is actually a state function. It does not depend on the path these people are taking, and therefore PV and T and U are all state functions. So let me explain further what does a state function and non-state function means. Let's imagine that we have some water here, and this water is at room temperature, which is around 20 degrees Celsius. So this is your T initial. So I want to raise this temperature to T final, which is equal to 80 degrees Celsius. Of course, you need a heat source or stove or some wood to do that. Now, you can do this process actually in two ways. You can do it in path, let's call it path A. You can do this in another path, let's call it path B, where maybe you made a mistake that you heated the water to, let's say, 90 degrees, and then you want to cool it down to 80. You can do that. So that's still called path B. Now, delta T in the first case is equal T final minus T initial, which is equal to 80 minus 20, which is 60 degrees Celsius. That's delta T. It's called delta TA. But delta TB is the same thing, because what you care here is your final temperature and initial temperature. Even if you heated the water to 90 and then you cool it down to 80, what delta T for B is T final minus T initial, which is again 80 minus 20, which is the same answer, 60 degrees Celsius. So in both cases, the answer is the same, and therefore the temperature, we call it is a state function. State function means it does not depend on the path that is taken. Now let us imagine that instead of talking about temperature here, we're going to talk about heat now. In thermodynamics, heat is referred by Q. Q is the symbol for heat in thermodynamics. You might agree with me that in path A, when you heated the water from 20 to 80, you paid some heat for that. You maybe spent some dollars with gas or heat source to heat up the water from 20 to 80. You can calculate that how much, and this is something we are going to calculate in this chapter, is the amount of heat provided when the water is going from 20 to 80. You can calculate actually that. But when you do that in path B, you raise the water to 90, and then you cool it down to 80. So the amount of heat in path B is different than A, because in path B you actually paid more money or paid more heat to do this process. Even if you cool that down, actually when you cool things down, even you want to pay more heat, maybe you want to put it in the freezer. So in path A and paths A and B, the Q is not is different, and therefore we say Q is non-state function because it depends in the path. So the take-home message here is that state functions and non-state function. So state functions, they do not depend on the path, while non-state functions, they depend on the path. So it's actually the other way around. State do not depend, non-state they depend. So example of state functions is P, V, and T. And you remember P, V, and RT, right? So I told you that this is called the equation of state, and therefore all the parameters in the P, V, and RT equation is actually a state function. After that, the U and the H, which are the internal energy and the enthalpy. These are all state functions. Non-state functions examples are Q and W, because both Q and the work they do depend on the path, and therefore they're non-state functions. Some argue that work is a state function. Well, here we are dealing with the thermodynamical work, which has a slightly different conception than physics, and therefore we deal with the work here as a non-state function. Okay, so the first law of thermodynamics, I mentioned that thermodynamics has 3 laws, first, the second, and the third. The first law of thermodynamics is another way to state the law of conservation of energy. It says that delta U is equal Q plus W. So where delta U is equal is called the internal energy of the system. It's measured in joules. Q is the heat and work, and W is the work. The addition of these two terms will give you the change in internal energy, which is delta U. So delta U is actually equal to the delta U for the system and the surrounding, and that will the delta U for the universe is actually delta U for the system and plus the delta U for the surrounding. Now, so and delta U is equal Q plus W. Delta U is the change in internal energy of the system. Q is the heat exchange between the system and the surrounding. You can measure that. And work is the work done or the work done by on the system. We're gonna come up in the next slide to define the work. The issue with this equation here is the signs. Now, for Q, which is the heat, we agreed that for exothermic reactions it's negative. For endothermic reaction, it's positive. So this is mentioned here in the table 6.1. If you look at the bottom of the table, it says heat absorbed by the system from the surrounding. This is endothermic reaction, and the sign will be plus. And if heat is absorbed by the surrounding from the system, that means the system is releasing heat. That's an exothermic, and that's a minus sign. Now, for the work, you cannot actually say work is absorbed or released because these terms are heat terms. The correct way to mention the work is says the work done by the system on the surrounding, or work done on the system by the surrounding. You can do so. The system can do work. Okay, it's like a car moving, and it does work on the surrounding, and therefore the work sign is negative. And if you are doing work, you are like, imagine yourself like a surrounding, and you're doing work on the system. In that case, the work is positive. Start here. Okay, so now let us move to define what work is. Recall from physics that work is actually the force times the distance. So this is the definition of work from physics. And we know also that the pressure is equal force over area. If you play with these equations, you come up with that the force is equal. So, sorry, from the second equation, P is equal Fa. That means the force is equal P times A. You just rearrange this equation, and you come up to the force is equal Pa. So that will tell you that the work is equal P times A times D, because the work is F times D. So I replace the F by Pa. And because of the fact that area and distance is volume, then we come up to this equation that work is equal PV. So, but if we are considering a change in work, that a system is doing work or work done on it, then the change in work at constant pressure is equal minus P delta V. So because the P is constant, the volume might change, then I come up to this equation with W is equal minus P delta V. So where this minus came from? This negative sign was imposed to reflect the physical understanding of work, as I am going to explain later. But this negative sign, it has been imposed here to get actually the right answer of work. So work at constant pressure, so there are different types of work in thermodynamics, but the one we are dealing with in Chemistry 101 here is that the work at constant pressure, where the pressure does not change, and the work will, in that case, will equal to P delta V, minus P delta V. Now imagine first that we are dealing with a work done by the system. To explain this, we start with a container that has some gas, and this gas has some volume, and it's under atmospheric pressure. We call it P. That gas container has a moving piston, so there is a small, a disc made of a metal sliding on the gas surface. That piston or that cover is free moving. It's allowed to move up and down with no effects. If this gas is allowed to expand, then that means its volume will expand from V initial to V final. The difference between V2 and V1 is the amount of delta V shown in the figure to the right. So the work done by this gas, because in this case the gas is doing work, and this is what's happening in the car engine, is that we are burning fuel in the car, so the gas expands and it moves some pistons, and the pistons move some gears, and the gears will allow the car to move. In this case, the car is doing the work, or the gas is doing the work on the surrounding. So in this case, we say that the work is equal to minus P delta V, and because of the fact that the delta V is a positive number, because the, V final is bigger than V initial, so delta V is equal to V final minus V initial, and you have a positive number, then when you plug in this equation, you will have a negative value for work. So work of the system is less than 0. So work done by the system, you have a negative work. That means work is a negative number. It's going to be -1, -2, whatever, because of this fact. Now imagine this is expansion. Imagine this is happening in reverse. You can draw these figures again, or actually you can just replace the words final and initial. So for compression, if you want to compress the gas, I mean you want to reduce its volume, you can start with a big volume and reduce it to a small volume. In this case, delta V is negative, because delta V is a small number minus a big number. And delta V is negative, the work will equal to minus P delta V. It's the same equation. The equation does not change. This formula here, work is equal minus P delta V, it does not change. But in the second case, which is the compression, delta V is negative, and therefore the work will be positive. So for a compression, work is positive because of the fact that we are doing work on the system. So here, I want to recap this again. So in this table, remember that work done by the system on the surrounding, it's also a negative sign, and work done on the system by the surrounding, it's a positive sign. In other words, the first one is expansion. It's when the work is expanding, the system is expanding, that's negative, and when the gas is compressing, that's positive. Let us move on and solve some exercises related to the pressure, to the work. It says a certain gas expands to a volume from 2 liters to 6 liters at constant temperature. Calculate the work done by the gas if it expands first against vacuum and second against constant pressure of 1.2 atmosphere. Allow me to solve B first, and then I will come back to A. So in B, we have work done against a constant pressure, and we know how to calculate that. So its work is equal minus P delta V, which is equal to the 1.2 atmosphere, which is the pressure, times delta V. So you have a volume changing from 2 to 6. So delta V means V final minus initial. V initial, that means it's 6 liter minus 2 liter. And that will equal to 1 point. So this is, don't forget there's a minus here. So it's minus 1.2 atmosphere multiplied by 6 minus 2 is 4 liter. So that will give you an answer of minus 4.8 atmosphere liter. So minus 4.8 atmosphere liter. This unit here, the atmosphere liter, is actually it's a unit of energy. It's not equal to joule, there is a conversion factor, but atmosphere liter is actually a unit of energy, just like calorie and joules and all that. So the answer is minus 4.8 atmosphere liter. It's negative because the system is expanding. So we are starting with a small volume and it goes to a big volume. The system is expanding, that means doing work on the surrounding, and therefore the work in that case is negative. Now let's go back to the case A, where it's expanding against vacuum. So if the system is expanding against vacuum, that means you have the gases here, and it has V initial, and suddenly it's expanding to vacuum. That means nothing. Okay? There is nothing in the vacuum. So work is equal minus B delta V, where you can calculate delta V. It's V final minus initial in vacuum, whatever the vacuum is, volume is. But the most important thing here is that the pressure in the vacuum is 0 because there is nothing in the vacuum. So when the gas expands to a vacuum, it's going to be subjected to a pressure, to no pressure, and therefore the work is equal to 0. In this case, we can understand this physically by saying when the gas is expanding against vacuum, there is nothing the gas will push at, and therefore there is no work done. Because it's expanding against vacuum, it's expanding against nothing. So there's nothing to push actually. There is no pistons, there is nothing to push, and we are not benefiting from this. There is no work done. The work is equal in that case to 0. So any work done against vacuum is 0. Now, what if we are interested in changing this number, the minus 4.8 atmosphere liter? I want this in units of joules. So the conversion unit is actually 1 atmosphere liter. It's equal 101.3 joules. This is the conversion factor between the two. So 1 atmosphere liter is not actually 1 joule. It's 101.3 joules. And if you want to change that, so this work, the minus 4.8 that we calculated in the previous example, you can just change it into joules by saying 4.8 atmosphere liter times the conversion factor, because 1 atmosphere liter is 101.3 joule. That will give you an answer of minus 486.24, let's say 24 joules. If you want to consider significant figures, this is actually 450 joules. The last question in this lecture is this question here. It says the work done when a gas is compressed in a cylinder. So we have a gas that is compressed, a compression, okay, is 462. So this number here is given to you, 460. So this is the work. Now in these type of questions, you want to impose the sign. This is a chapter that you want to think about these numbers, and you decide to put a negative or positive based on your understanding to the equation. Usually the numbers will be given to you in a positive value, but sometimes these numbers are negative and sometimes are positive. Now you want to understand what's going on here. This is compression. In compression, when the gas is compressed, the gas does not compress by itself. Somebody has to compress it, and therefore compression, it's work done on the system. So we have work done on the system, and therefore it's positive. So we leave this number as positive. And actually, I like you actually here to put plus to reinforce the idea that you understand this is compression. Now, there is also a heat transfer of 128 joules from the gas to the surroundings. So Q here, and I guess you know where I'm going here with this. So 128 joule, but this is negative. Why? I changed to negative because this is a heat that is transferring from the gas from the system to the surrounding, and it's exothermic. Even in this question, it does not say negative 128. You must put the sign, you must impose the sign. So here you need to impose the sign. That means based on your understanding of the question, you need to impose the sign, and you want to put negative or positive based on your understanding. Calculate the energy change for this process. So the energy change, that means delta U is equal Q plus W, which is equal to minus 128 plus 462, all of them are in joules, and the answer will be 334 joules. Someone will just go ahead and add these numbers actually, 462 plus 128, and you will get to something that is maybe 550, but that's a wrong answer. Because in this question, there's compression, that means the work is positive, but there is an exothermic process, that means the heat is negative. And when you add this to that, you will find the answer to be 334 joules. So by this, I finish my lecture for today. I wish you enjoyed it, and looking forward to your discussions. Thank you, and have a great day.